Hi guys, welcome to Unit 7 Notes B. Today we're going to learn how to do icebox problems. The I stands for the initial, the C stands for the change, and the E stands for the equilibrium. We're going to compare concentrations at the initial and the equilibrium, use the change in one of the either reactants or products, usually the products, and then we'll be able to use that X that we've solved for to find the missing concentrations. First, let's look at how the wording of the problems are going to be a little bit different from what we've already seen. The first sentence tells us what we have when the reaction initially begins. 4 moles of hydrogen gas and 6 moles of chlorine gas. Of course, you would have 0 moles of product when you first start the reaction. We need molarities, so we do need to consider the volume, which will stay constant throughout the reaction. And we can convert each of these initial moles into molarities now. So by dividing the moles by the liters, we can take our 4 moles of H2 and turn that into a 2 molar concentration, and our 6 moles of Cl2 into a 3 molar concentration, since there are 2 liters of solution. One thing that comes from a more conceptual understanding is the concentration of the product. When the reaction is initially starting, there is no product, so 0 moles, 0 molarity. In the second sentence, we see an indication that there is some time that has passed, because it says we're at some time later. Now we know that a system likes to be at equilibrium, that is a stable and natural state that would naturally progress. And so we can make the assumption that if we're looking at the later time, then the system would be at equilibrium at that time. And so the only information we have at that time is the concentration of the products, given that there are 2 moles of HCl gas, and assuming that you still have a 2-liter volume, you can find that concentration. So that becomes a 1 molar solution. However, you can't make any assumptions about the concentration of the reactants yet. Let's set up our first icebox. To do this, you write the equation across the top of the box, and you write I, C, and E down the side of the box. We're going to literally be adding the I and the C in order to get the E, so I like to have this line down here as well. Next, we'll plug in the initial concentrations that we found from the first sentence. 2 molar hydrogen, 3 molar chlorine, and then no product, so 0 molar for the HCl. We can also plug in the 1 equilibrium concentration we were able to find, the 1 molar HCl. The next thing that we want to find is the change, and this is based on molar ratios. If we have 1 mole of reactant each, but 2 moles of product, then if we let X represent the change, we should get twice the change in product as we do for each reactant, since it's a 1 to 2 molar ratio. The other thing you have to consider is that the reactants are decreasing, whereas the products are increasing as the reaction progresses. So we represent that with negative signs for the reactants and positive signs for the products. Now we can use the one thing that we have an entire completed column for, our products, to set this up like an algebraic formula. 0 plus 2x equals 1. And then, of course, solving for x gives us 0.5. Now that we know what x is, we can use that to find our other equilibriums by plugging in 0.5 for x. So let's do the hydrogen first. If we have 2 minus x, and then we plug in the 0.5 for the x, we find that the equilibrium concentration for H2 is 1.5. And finally, let's do the chlorine. We have 3 minus x that we're trying to solve for, and if we treat x as 0.5, then we find our new equilibrium concentration of 2.5. Now the point of all of this was to find the equilibrium concentrations so that we can use those to find our equilibrium constant. The next step would be to write an equilibrium expression, where you have the products over the reactants using the coefficients as the exponents. Now all that's left is to plug in our new equilibrium concentrations. When we plug in these concentrations and solve, we get a Kc equal to 0.3. Keep in mind the meaning behind this. When we get a decimal or a Kc of less than 1, we are favoring reactants at that equilibrium, meaning there would be more reactants than products at the equilibrium. Let's try another one, where again, we're not given all the equilibrium concentrations, we have to find some of them from the initial concentrations. In this problem, the first sentence allows us to form our balanced equation. The oxidation of NO to form NO2 means that NO is going to react with diatomic oxygen to form the nitrogen dioxide, and then we just have to balance that with a couple of 2's. The next sentence gives us our initial concentrations for the two reactants. The NO and the O2 both have 0.6 moles, and they are both in a 2 decimeter cubed or 2 liter container. So both reactants end up being 0.3 molar initially. Keep in mind, we know also that there's no product when the reaction initially begins, so we have a 0 molar product. Next, we're finally given some information about a concentration in equilibrium, but only for the NO2. We have 0.2 moles of the NO2, and we would assume the volume is still constant. And that gives us a 0.1 molar product at equilibrium. Next, we're going to set up our icebox, and then plug in the concentrations that we were able to figure out, which is going to be all of the initial concentrations and then the equilibria concentration of our product. Next, we'll work on our change row. We want to look at how the change, which we will let be x, is related to the molar ratio. So for both the NO and the NO2, I'm going to have twice the change as I would with O, which has a coefficient of just 1. For our reactants, we're going to be decreasing by that amount, and for our product, we will be increasing by that amount. So now that we know how they'll change in relation to each other, we can use what we can, this column of products here, to solve for x, and then use that x in our reactants. So setting this up, we have 0 plus 2x equals 0.1, and so 0.1 divided by 2 gives an x of 0.05. Now we can use this x on the reactant side. First, let's use that for the nitrogen monoxide, so 0.3 minus 2x, and then if I let x be 0.05, but I double that to 0.1, 0.3 minus 0.1 is 0.2. So our equilibrium concentration for the nitrogen monoxide is 0.2 molar. And finally, for our oxygen, we have 0.3 minus x, so 0.3 minus 0.05 leaves 0.25. So that's our equilibrium concentration for the oxygen. Now that I have all of my equilibrium concentrations, I can plug them into the equilibrium expression to solve for K. The next step is to set up the equilibrium expression with products over reactants using the coefficients as the exponents. Now we just need to plug in those concentrations. By plugging in our new concentrations and solving, we get a Kc equal to 1. Which actually means it doesn't favor the reactants or the products. So we just so happen to have an equilibrium where we have an equal amount of both. Here it is all nice and typed up. I just wanted to point out I should have kept the 2 sig figs, so it should actually be 1.0. Next, we're going to look at a slightly different type of this question. This time we're going to be given the K, the actual equilibrium constant value, and we're going to work backwards to solve for some missing concentrations. In this part, the math can get a little bit trickier. Let's look at what they're giving us this time. The first sentence here gives us a value for Kc to be equal to 6.78, which is what we had calculated in the last two, so we can tell already this is going to be a different type of question. It also gives us the complete balanced equation where we can see it's already perfectly balanced and everything has a 1-to-1 mole ratio. So we're just going to see the change as decreasing reactants and increasing products at equal ratios. The next sentence actually gives us the initial concentrations already calculated into molarity or moles per decimeter cubed. And then we can see we're solving for the equilibrium concentrations themselves. So the first couple things we need to do is to set up the icebox in general and to look at what the equilibrium expression would be so that we can kind of put the two things together. So we'll start by setting up the icebox, writing the entire equation on the top and then the ICE down the side. Now we'll plug in what we can, which for this problem will be the initial concentrations. we were given the initial concentrations of the reactants, the 0.03, and then you should conceptually know that there would be no product. So we also have the zeros on the product side that we know. We also know the mole ratios, so we can start putting together the change row. Since there are no coefficients in this reaction, these are going to be changing by the exact same amount, 1 mole to 1 mole. The only difference is the reactants would be decreasing by this amount and the products would be increasing by this amount. So we have positives and negative x's across the board. What we're not given at all is anything for the equilibrium row. So we're going to need to kind of put this together algebraically, where we can set this up on the reactant side to be equal to 0.03 minus x. So we know whatever the concentration at equilibrium for SO3 is would be equal to 0.03 minus x. Same for the NO. So both of those reactants are equal to 0.03 minus x. And then for the products, it's just 0 plus x, or just x for each of the products. So we have 4 concentrations at equilibrium, but written in relation to x. Now let's look at our equilibrium expression, where we say Kc, set it equal to the products over the reactants using the 1 coefficients as the exponents, therefore meaning there are no exponents, or the exponent is just 1. And what we're going to need to do next is plug in the equilibrium concentrations we found as x's into this side of the equation. And then we'll keep our original k, which we were actually given as a value, and plug that into the left side. Then we'll be able to solve for x. So I'm going to take my equilibrium expression and start plugging things in, starting with the given Kc, which just goes as Kc on the left-hand side. Now I want to plug all my x variables in on the right side. Each of the products was just x, and each of the reactants was 0.03 minus x. So essentially I have 6.78 is equal to x squared over 0.03 minus x squared. Now our job is just to solve for x. So I'm going to go ahead and find the square root of both sides to simplify this a bit, and then I'm going to multiply that by what we have in our bottom here of the 0.03 minus x. So first the square root of 6.78 is 2.60, and then we're going to distribute that. So we have 2.60 times 0.03 is 0.0781 minus the x times the 2.60, or 2.60x. So now we need to get x all on one side of the equation, so I'm going to add 2.60x. So now I have 3.60x. Now I want to isolate x, so I'm going to divide by that. And finally, I find that x is equal to 0.0217. But I'm not done yet. I have to use this x to go back and find those concentrations. So that's what we were actually looking for, is the equilibrium concentrations. Now we're going to use x to find those concentrations. For the products, their concentrations were just equal to x, because it was 0 plus x equals x. So those concentrations are just 0.0217 molar. But for the reactants, we have a little math to do. Remember, for the reactants, we had 0.03 minus x. So we're going to do 0.03 minus the 0.0217, and we get 0.00830 molarity for both of the reactants. Next, I want to look at an example where we can take a little bit of a shortcut. You can't always take this shortcut, and we'll go into a lot more detail when we get into the acid and base equilibrium about when this comes in handy. And I wanted to kind of go ahead and show you how it works. The wording of this question is very similar to the one we just did, so let's start by looking at those similarities. It says that we have a small value for the K, and it's given to be 7.31 times 10 to the negative 18th. Notice how small that is. That's how this problem is different. But it is the same in the sense that we're just going to plug that into the left side of the equation here as Kc in our equilibrium expression, which is still set up as product over reactant, just making sure you include those coefficients as the exponents there. So we're given the balanced equation so we can get our mole ratios to help us with the change row. And we're also given the initial concentration of what in this case is just the only reactant of the water. So let's start by plugging in what we can. So first we can fill out the initial row. We have our initial concentration of water given at 0.10, and we know we have 0 products initially. Now we can do our change column where we look at the relationship, letting that be x of the change, keeping in mind if we have a coefficient, for example the 2 on the water and the hydrogen gas, that would double the change, and the reactant will be decreasing by that much and our products will be increasing by that much. So now we have our change column, minus 2x for the water, plus 2x for the hydrogen, and plus x for the oxygen. What we don't have is much about the equilibrium. So let's do kind of like what we did last time and just let it be a version of x. So if we kind of add up for each column, for the water we get 0.1 minus 2x, for the hydrogen it's just 2x, and for the oxygen it's just x. And then what we did last time is plug in these concentrations as versions of x into the right side of the Kc expression and plugged in the given value for Kc into the left side. And then we solve for x. So far it's the same as last time. Now here's the shortcut. We are able to basically assume that the x in relation to 0.1 molar concentration is essentially negligible because the Kc is very small. And I mean double-digit negative exponent small. So when it's given that the Kc is very small, we can essentially just ignore this minus 2x because we would assume that given the sig figs in comparison to the 0.1 molar, that no noticeable change would be observed. Now you cannot do that to the products because anything would be measurable or not negligible in comparison to 0. It's only negligible in comparison to the 0.1. There's a general rule of thumb that there needs to be a less than 5% difference from the value that you would get if you did solve it all the way through with x, and that's something we'll look at a little bit more when we get to the acids and base unit. But for now, it is one shortcut I just kind of wanted to introduce, that only in relationship to a given concentration, when the Kc is actually very small, you can ignore that x, which makes the math a little bit easier to solve. Now I want to take my equilibrium expression and start plugging things in. So I've got my Kc plugged in on the left, the 7.3 times 10 to the negative 18th, and on the right I'm going to plug in those concentrations using the equilibrium versions, where for the products I have versions of x still, the 2x for the hydrogen and just the x for the oxygen. And then for the reactant, we have just the 0.1. We don't have to worry about the minus 2x because we've deemed that negligible. So I'm going to square the 0.1 on the bottom and multiply that by the 7.3 times 10 to the negative 18th, getting 7.3 times 10 to the negative 20, getting this out of the denominator. And then our numerator, 2x squared, will become 4x squared, and then multiply by that by another x, and you get 4x to the third. So now to isolate x, we need to divide by 4 and take the cubed root. So working out that math, we get 2.63 times 10 to the negative 7th for x. Now we just need to plug that in to solve for our oxygen, which of course is just going to be that number, but we also need to double it for the hydrogen. So the concentration of oxygen at equilibrium would be the 2.63 times 10 to the negative 7th, and the concentration of hydrogen at equilibrium would be double that, so 5.3 times 10 to the negative 7th. The question specifically asked for the hydrogen concentration, so our answer is this 5.3 times 10 to the negative 7th, and the units would be molarity or moles per decimeter cubed. We have one last thing to look at today, and that's how Gibbs free energy can tell us how the reaction will proceed. So we've talked before about spontaneity with Gibbs free energy. Where delta G is negative, it means it is spontaneous and the reaction is going to happen, but we never talked about how that means it's going to happen in the forward direction. Whereas if delta G is positive, we said that was not spontaneous, so that reaction is not happening in the forward reaction. Instead, it is proceeding in the reverse reaction. Whereas if delta G is actually 0, then the reaction is at equilibrium. Let's take a second to put a few things together. We've talked about how if Q is less than K, then the reaction proceeds in the forward direction, and if K is less than Q, it would move forward in the reverse reaction. What we're really trying to achieve at equilibrium, this low energy stable state, is a delta G of 0, so a minimum value of the Gibbs free energy, and then also where Q is equal to K, representing a maximum value of entropy. Chaos. Nature loves chaos, second law of thermodynamics. So we want a very high chaos, but low Gibbs free energy moment, and that would be the perfect equilibrium time. We do have a formula, and it is given to you in the data booklet, that can relate the equilibrium constant K to Gibbs free energy G, and it is dependent on the temperature and of course our universal gas law constant. In our last question, we're given delta G and we are asked for the equilibrium constant. So if you see both of these things in one question, you know you need our new formula here. So we're simply going to plug in our G. We should know R, our universal gas law constant, and then they will also tell you the temperature. Notice this is standard for thermo. And we're going to plug in the temperature and be able to isolate K. So I have it all plugged in here. I have the G in purple on the left, minus R, which is that given gas law constant of 8.31. The temperature, which was given in Kelvin, you do want to make sure that it is, so our units will cancel here. And then the ln of K, not Kelvin, but the equilibrium constant K, which I left in green. So now I want to start trying to simplify the math on this. So I'm going to go ahead and divide by all of these numbers to get just the ln of K on the side. First of all, when I divide negative by negative, it's going to become positive. And then math-wise, we're going to get our answer equal to ln of K. Before I do that, though, we have to make sure that the units are the same, not just for the Kelvin, but also, right now we have G in kilojoules, and the R was given in joules. So I'm going to go ahead and convert the G to joules, so from 4.38 kilojoules to 4,380 joules per mole. That way, when I divide by the R and the temperature, I can get the joules and the moles to cancel. So all of that becomes 1.77. The units are all canceled. Now we can set that equal to all that's left on the right hand side, which was the natural log of K. To solve for K, we're going to need to find the anti-natural log. So basically we need to find e raised to the 1.77 power, and we get 5.87 as our final answer. So that means our equilibrium constant, K, is equal to 5.877. Remember, there are no units for K. This is simply our final answer. Alright guys, that'll do it for Unit 7, Notes B.